dealing with condition, a lock, the condition itself, and in this case a simple int variable, but can be a structure or more than one int. Okay, that's the condition. That is used in mutual exclusion of the lock by the condition. So, in this case, we have 3 threads, and this count set to 10, and count limit set to 12. And what we want to do here in this example is to make a thread wait until the condition that the count reaches the limit 10 is satisfied. So typically you wait a condition to happen. So you signal a condition when the condition is satisfied. Okay, it's a little bit different with respect to semaphores. Okay, so normally you are sure that someone is waiting on a condition, and you signal the condition when it is fulfilled. Okay, so in this example, what we have is a main that creates 2 increment counter threads and a watch count thread. Then it simply exits. So you have 3 threads in total. Before we buff standard out as usual, and we initialize the mutex in the condition, the lock, and the condition itself. Okay. So since we have declared, I hope, here the condition, okay, and this is a global variable, this int is initialized to 0, okay? So what happens with the count thread? For 10 times in mutual exclusion increments the count, okay, so the variable that is common with the watch thread, and then tests in mutual exclusion the count limit, okay, if it is 12 or not. If it is 12, it signals on this condition. But initially, of course, the counter is 0, 1, 2, etc. So I will come back on this. It's better to analyze before the watch count. So the watch count starts in mutual exclusion, controls the counter value. If it is less than the count limit, it waits. So remember that the wait of the condition is always blocking. Okay, it's always blocking. And we pass as the first argument the condition. Why we pass also the address of the pointer to the lock? Because you know that when this wait is performed by this process, this thread goes in the suspended state, and the lock is unlocked. Here it was locked, and here is automatically unlocked. Otherwise, no one can increment the counter, okay? Because the counter is incremented in mutual exclusion using the same lock. So, this is the watching thread, that waits until this count limit is reached, and the other two threads in mutual exclusion increment the counter, and when the count limit is reached, one of them signal to the condition. What happens? Of course, this condition must be checked in mutual exclusion, okay? And it is a responsibility of the programmer to unlock the lock. What happens to the watching watch count thread? It was blocked here. When the signal is received, okay, it prints this sentence here. At this point, the lock is locked. So when the thread wakes up, it wakes up with the lock locked, so that it can perform many operations here before unlocking. So before allowing other threads to do their job. Okay? Okay. Can you do another round? Okay. Is it okay? Yes.
Because before the if is locked.
Yes.
And after the if is unlocked. But,
So follow me. Time is going on. So this is locked. At this point is unlocked. When this thread is blocked, the lock must be unlocked. Otherwise, the increment thread will not increment the counter. When it wakes up, because a signal has been performed, this operation is done with the lock locked.
So the watch once has calculated the signal to the count lock, to the count thread.
Yes.
Ah,
No, this is the watch count receives the signal here from the first thread that set the count to 12 in our case, send the signal with the conditional signal here. So the watching thread is waiting the event that the counter reaches this count limit. Okay? So this conditional signal awakes the
only in case
Only-
the limits and the signal.
yes, and we are sure because this is done in mutual exclusion. Okay? Well, now I want to show you again the producer and consumer solution with semaphores and with condition to show you the difference. So, and which are the advantages and yes.
I have a question. When the income contract does the research condition plan, it did not release the law yet.
Yes.
So,
Yeah.
yes.
Yes, this condition is done with the lock locked. Okay. So it's like this thread passing the lock to the receiving thread.
Yeah,
Okay.
but what if this thread has to do a lot of work before passing the law?
Because okay, both have to unlock to be sure. So in any case, the unlock is not a problem, of course, even if you do it 2 times. If you do lock 2 times, it is a problem, but unlock is not a problem. Okay? So it's always like this, the template. So you have 4 the signaling thread, the pair lock and lock, and for the receiving waiting thread also the unlock. So that is.
Is it a signal that unlocks the
Sorry?
Is it a signal that unlocks or is it the previous
So the signal does not unlock the lock, okay? Does not unlock the lock. After this, it does the unlock, okay? So in this piece of code, as a matter of fact, still this thread has the control of the lock. Only when the wait makes, when the thread that is blocked on the way awakes, it collects takes the lock and continues. By the way, you use always this protocol to be sure. What is important is that the wait awakes the lock.
Can we go back again to the watch?
Yes. Yeah.
So on the way.
On the way.
Can you explain again what the
Okay. I don't understand why you are so. Well, there is a kernel. The kernel makes the thread go to the block state. Okay. Okay. What happens to this lock is locked. Okay. If the kernel doesn't unlock the lock, no other thread may use the count. It's okay?
But I don't understand why we why we wait only if the count is less than the limit, we wait.
Yes. Yes.
And then we are on the wait and we wait for the signal.
So this is yes. So the synchronization is I wait for an event and then a signal is performed to signal that this event happened.
But the wait doesn't unlock it.
The wait?
Once the wait has been performed, it doesn't unlock it. The unlock is done after.
After, yes. Yes, after this, when the thread is blocked here, this lock is locked, it's unlocked. When you pass here, this region is done with the lock locking. This is a simple example, but the other, producer and consumer, may be explain you better, which are well the advantages of condition, because in this case, well, it is not so important, yes, to use the condition in this situation, because you can check it with a simple mutual exclusion. But let us recall the producer and consumer protocol. So we have a buffer of limited dimensions, 16 elements. In our case, an int of int elements. And we have the empty and full semaphores. And since we imagine that there is only a single producer and a single consumer, we don't need any other mutual exclusion semaphores. In this example, you have exactly the same code that I wrote and here on the slide as a pseudocode. So you have in and out that are global variables, and the producer uses this put function that does the semaphore wait on the semaphore empty, okay, initialized to the dimension of the buffer, so that we can pass this wait 16 times in our case. Then we put the data where the in index says in the buffer, increments the in so that it implements with this module operation the circular buffer. So when in goes to the position 15, that is the last, the next position will be 0. 15 plus 1 is 16, divided by 16 goes to 0. Then it posts signal on the semaphore full initialized to 0 to indicate that a position has been filled. The get operation is dual. So the full is initialized to 0, so the consumer that does away get blocks here if producer didn't produce anything, and does the same thing. So takes from out the data, increments out, and signal on empty. Okay? So we have these semaphores, two semaphores, and in practice we exploit the counter of the semaphore to understand if there is something on the buffer or there is nothing on the buffer, okay? But this is strange in some way, no? Because to understand this code, we have to read this get and put in parallel, okay? Because otherwise I don't know what this same post means, okay? So when I write the producer and consumer solution, I typically write in parallel the two. If you remember, I wrote the consumer first with this weight full, because we understand that if full is 0, the consumer blocks immediately. Then I said, well, how many times we can call, in this case, put exactly buffer size, because the semaphore empty is initialized to buffer size. And then the producer uses put. In this case, this example, it generates 10,000 numbers, and then put it, and finally put -1 over this -1 on the buffer to terminate. The consumer use get to get the number, then if d is equal to over, press this loop forever. Okay? So this is the solution with the semaphores. Now we look at the solution with conditions. Okay, so the solution with conditions, the framework of course is the same. Simply here I use a structure. In and output and out are now read position and write position. But notice that I added a variable count. So this is the first difference between the solution with semaphores and with conditions. Then we have two conditions, exactly as we had two semaphores. Okay, not empty, not full. Okay, so initialize the buffer, mutex init the lock, not empty, not full, always null. Okay, so we have two conditions initialized and the lock variable initialized. This lock is, as a matter of fact, used for protecting the variable count. Okay? So the lock protects the variable count, but also this. But this read position is used only by a single producer, consumer, and this write position is used only by the producer. So, as a matter of fact, the lock, as we saw before, is used to lock the region where the count is modified or tested, okay, to protect the condition.
But in case we have many producer and many consumer,
We have to do to use additional locking. Exactly.
As a structure.
Well, we will see. We will see now if it is true or not. But it's true. So now let us begin as usual with the get. In mutual exclusion, lock here, notice this is the correct way always to use to test the condition, not if but while. While, a single instruction, a single way. Why? Because, and this is important, and here you understand why the condition wait, when when the spread pass the condition wait, it's important to have the lock locked, because immediately we test the condition. Okay? If this weight, after this weight, this spread awakes without the lock, it has to go back at this point. Okay? While you can always write, this is another template, while condition, logical condition, wait. In this way, if you are sure when you pass this that this condition is not true, okay? You are not blocked here. So if count is equal to 0, you wait. Otherwise, you can pass. Okay, so looking at this solution, you immediately understand the difference between the solution with semaphores and with condition. Here, you immediately see which is the blocking condition. The blocking condition is when the count is equal to 0. Exactly what we say in Word when we state the specification of producer and consumer. If the elements, there are no elements in the buffer, you wait. You don't need to look at the code of the producer. Okay? Then, if the counter is greater than 0, you are sure that there is something that you can read, and so here is the alternative to the modular arithmetic for implementing the circular buffer, but I prefer the other solution. And we count minus minus. Okay? So, since an element has been consumed by this get, it signal on the semaphore not full and unlocks. Okay? Of course, the put operation of function is dual. A mutual exclusion on the same lock. If count is equal buffer size is full. Okay? So conditional way here, same loop and same operations. So the conditions allows us to use logical conditions, logical expression that can be complex and then be not easily implemented with one or more semaphores. So you put in a logical condition the condition for waiting, and then you wait. When the variables that are included in this logical condition change, another thread may signal that this condition is true. And so the waiting thread may proceed. So the advantage of a condition is that they are more powerful to solve some problems and to describe which are the waiting conditions. What we lose for this, we lose some efficiency, because as you can see here, put and get are executed in mutual exclusion, because they begin by pthread mutex lock on the same lock. So, if while the solution with semaphores allows me to read and write at the same time because if the buffer is not full and not empty, so in points here and out, points here. So since they don't point to the same element, a producer and a consumer may work at the same time. So I can put and get at the same time in concurrency. While in the using conditions, of course, I cannot do the hit, because both work on modular exclusion.
Why we use why? Why we cannot use if instead of why?
Oh, because, well, in this case, because you don't know, as I said, this is a template, because it is possible that after this wait, more than one thread, you have to wait a little bit. I will explain that you have a system called broadcast. So if you have a many thread waiting on the same condition name, you don't know if the condition is true for one of them or two of them or all of them.
Instead, in the case of one thread,
You can use if. Yes. Okay, so try condition. Try condition is an example here where we pass three arguments, the number of condition signals that we want to send, sleep time for the main thread, and sleep time for the created thread. So we get these three arguments at the beginning, then the main thread creates this thread A, and sleeps exactly this number of seconds. Then n times it prints wake up thread A, mutual exclusion as normal. It does the conditional signal, unlock, lock, etc. Then the thread A sleeps the seconds passed as argument. A mutual exclusion says thread blocked, just to inform us, and that's the conditional wait. And when it wakes up, prints a thread as being sealed. So if we run this, where the condition ls, yes, dot slash try condition, of course, remembers me that I must give, let us begin with 1, and then I do the normal case, where the sleep time for the main is greater than, so both 5 and 3. So the thread is blocked, wake up at thread A, and the second, since this does a forever loop, it blocks, and that's all. Okay? Control C. Now, what happens if I do the inverse? So I make the main thread signal before the wait has been performed. Wake up the day, thread blocked. Okay? So it's not like semaphores, wait and signal, where we have the counter and the number of signals that have been sent is remembered in the counter of the semaphore that is incremented by 1. In this case, this is blocked, so you must be sure that the condition where you are waiting will be receive a signal after some time. Of course, if I put here 4, for example, 4 times, thread blocked gives 4 signal, but just 1 is received. Okay? So there is no memory of the number of signals that have been sent and not yet received. Okay? Condition timed wait is like the try wait of a normal semaphore. In this case, we create a thread, and then a module exclusion. You use a thread condition timed way. In this case, since we use a time null plus 2, means that this condition will be, the thread will be blocked on this condition for a maximum of 2 seconds or until another thread does the signal. Here you have an hibernation argument passed as the first argument of this program, and playing with this you will obtain a condition time wait timeout or not. Okay. By the way, I have to do many other things, so you can try it. Try broadcast instead. Here we have a given a number of threads that are created, and after 5 seconds, the main thread set this variable condition met to 1, and wake up all the threads using the thread condition broadcast. So every thread has a wait on the same condition. Okay? So if we want to wake up all these threads, we must use the thread condition broadcast, not just a single signal. Okay? Of course, again, while we use, and this is more meaningful here, in this case we use a single condition for this thread, but we may have a different condition for different threads. So it is important that when you wake up all the thread retest the condition to see if the condition is met or not. Okay, for them. So you have, let's say, 10 threads waiting on different variables or on different values in the logical condition, and that's why we use this while. So every thread wakes up. Every thread in module exclusion one at a time tests the condition. If the condition is still false for that thread, it goes to the block state again. Maybe at least one should go on, because otherwise the program is incorrect. So otherwise we have not to use the signal and the broadcast. Okay. Well, so that's all. We'll play in laboratory with conditions. Now, main memory. So far, we concentrate on processes and synchronization, but as you know, to run a process needs to have the code and the data in memory. So the problem is that we want to use the main memory and to share the main memory among threads or processes. So the first part of this module, we will look at the say organization of memory, and the second part we will see how we can implement virtual memory. What is virtual memory? virtual memory means that we have a memory that has the same characteristics of the main memory. Okay, it's a little bit slower, but has the dimensions that can be as large as a complete disk or other storage, large storage, mass storage. So how it is possible? And the cost, of course, the cost is the cost of the disk, not the memory. Memory costs more per byte than disk. So virtualization, as always, means that we have something that is physical, and we virtualize this physical device in a way that makes it better, larger in this case, but more or less with the same access time. This is a virtualization, okay? So, first we look at the basic concepts, and then I would like to concentrate on paging. That, of course, you should know. It's the organization of all the memory management units of modern hardware. Okay, so let us see which is the architecture, the main architecture. So here you have the CPU, okay, and in the CPU you have registers, and when the CPU access register has no delay and works with the maximum speed, clocked up. Then here you have the main memory. And in between, you have cache memory. So what is cache memory? A cache memory is a special memory, not so special, but that is managed in a different way by hardware with respect to the main memory. So the idea is that the basic idea that allows to speed up the access to main memory is the so-called locality. And space. I have a nice picture, but I don't want to lose time. What does it mean, locality of reference in time and space? It means that when you run a program, okay, and the program counter, okay, doesn't jump randomly. In this location, this and then, okay, typically as a pattern of execution, or sequentially, a jump, when there is an if, and loops, okay? But it is not random. Second, when a program runs, it uses some data, maybe arrays or matrices, So it's extremely probable that when you have done a reference to the first element of the array, the next element will be the second, or the third, and so on. So there will be locality in time, because the program counter goes linearly on or with loops, and in space, because you typically process data structures that are stored contiguously on memory. Okay, so if you look at the snapshot of the memory in time, so here you have addresses, and here you have time. Maybe you see that there are regions clustered in this way. So at this point, my program is working on this data, on these instructions, then it goes here, maybe then jumps into a function, okay, so other addresses, and then you will see probably something like this growing because it's processing an array, or other thing like this, processing a matrix, okay? By the way, what is sure is that there are clusters, not a gray pattern, random pattern. So locality allows us to exploiting locality. We can obtain a fast access to main memory. How? If the CPU make a reference to say this byte, because CPU generates addresses and address, so an address is a byte, the minimum amount of information that you access in memory is the byte. And that means that this information, 1 byte, 4 byte, 8 byte, passes always through the register before the CPU may process it, okay? You always load internal memory of the CPU registers the content of an external variable that is stored in main memory. So this takes some time, nanoseconds, but much more than the time needed to process it in the registers. So rather than since there is the locality, space and time locality, by hardware, when you read for the first time this element, as a matter of fact, you read a bunch of memory, so a line of memory that you copy in this fast memory, okay? Memory cache. So this is called cache memory because it's hidden to the programmer. It's transparent to the programmer. It's used by hardware just for speeding up the access. So for the next reference, it's extremely probable that this data will be found here. So the access time will be not the one in main memory, but the time in the cache memory. Okay? This is computer architecture. Then, what about the kernel now? The same virtualization that we did, that I explained now, so it's a virtualization of a main memory, can be done for the disk, for the mass storage, because here you have the disk, and you know that even if this now solid state is not as fast as the main memory, of course. And so we can reproduce the same strategy due to locality properties also for the mass storage, reserving in main memory what we call the buffer cache. So part of the kernel memory, is reserved for virtualizing the disk. So exactly as cache memory virtualize the main memory, part of the kernel memory virtualize the disk, so that the access time to the disk reduces, because many times the CPU will find here and here the data, and only with less probability has to go on the disk. When it enters at the disk, it will read one block of data, or even two blocks. Maybe the block that it immediately needs, and it reads ahead, as we will see. Okay, to even help finding the data, speculating the future. Okay. So this is the hierarchy of memory management, and of course many of these things are done in hardware, but other, of course, must be appropriately set up by the kernel. The second problem with memory management, of course, is sharing. Since the same memories shared among processes or threads, you have to protect memory from unauthorized access, and even from your own errors, violation of the domain. Okay. Okay, the simplest way of protecting the domain of a process, so this is history. So you have a process and you have two registers, hardware registers, base and limit, and you have the hardware, a simple hardware that compares the addresses generated by the CPU to see if it is out of these two boundaries. Okay. This, of course, is the first and immediate organization that you may have in mind that has been implemented, but has its limitation, because this was done for CPUs that generate absolute addresses, okay? While instead, modern CPU generates always relative to zero addresses. Okay, let us go on here. And so, what means generating relative to zero addresses? It means that a programmer and a compiler see the location of the instruction and of the data as logical addresses. A logical address is the first instruction start at location 0, okay? And the next instruction will be at location 4 and so on. But of course the kernel has to manage and to map the logical address to a physical address. And this is done by the memory management unit. The simplest way, but a big step forward, has been done with this concept, because the CPU generates relative addresses, but the hardware, together with the software, the hardware offers an additional register, the relocation register. This value is loaded by the kernel when this process takes the control of the CPU. So at the context switching, this relocation register is set up, in this case, to 14,000. Okay. Of course, no user may change the content of this register. It's protected. When CPU generates 346 as an address, this is simply added to the relocation register value to produce the physical memory. Okay? So in this way, you compile always in a logical address space, and as the name says, the kernel relocates your code and your data according to its strategy and where there is in main memory a free region that is able to keep code and data. Okay. Of course, we need still the limit register to avoid going out of the region, of the main region. Checking the bound of this domain is easy, because every address that is negative, of course, is incorrect. And checking with the limit register is very easy with a comparator. Yes, dynamic loading. Dynamic link. Of course, the first computers had limited memory. Still, they were able to perform tasks like editing, compiling, etc. How they did? Of course, using some form of dynamic loading in memory from the disk. Okay, this can be done at runtime. You know that you can compile, and we will, as a matter of fact, compile a shared library in laboratory. So some piece of code that not necessarily enter to the executable of your program, but can be loaded either by you as a module or dynamically when it is necessary. So it doesn't waste physical memory. For example, you may have a module that contains all the indication of errors, for example. Typically your program will be correct, so it's not necessary to load this code, but if an error occurs, you think, well, you would like to know which is the error, so this can be loaded. Second important concept is swapping. Okay, what does it mean swapping? Swapping means that we have not only main memory but also some external memory. What I call a backing store. Backing store typically is a disk or a partition of the disk, and the one that you use also when you partition your disk for Linux, for example, of the swapping file in Windows. So why I call it the backing store? Because it is managed in a completely different way with respect to the file system. Okay? The file system, you have files that are created, destroyed, etc., small files. While in the backing store, the management is done to move many blocks of data as fast as possible from memory to disk and vice versa. So having devoting some disk space to the backing store and adding disks with enough throughput, fast enough, even in the 60s of the last century, it was possible to run maybe 50 users, okay, at the same time, so multi-users on machine of that times. Okay, so the concepts are always the same, but of course the technology changes, and we always proceed by introducing maybe concepts that were older but adapted to the new technology. So without some technology, you cannot have some type of concepts. Okay, if you, for example, if you don't have enough throughput for the disk, you cannot have in swapping. You cannot have multi-programming. So, what is swapping? Swapping essentially means that after a given amount of time, not only the CPU is switched from one process to another process, but also to allow many users to run, to share the resources of the system, the entire image of a process is swapped out, so put on the disk, the backing store, and the entire image of another process of the same user or different user is swapped in memory. Of course, this must be very fast and done through the DMA. In the modern system, this still happens, but not with the granularity of the process image, but with the granularity of the pages. Okay, so in virtual memory we will see that it is not necessary to keep in memory all the data and all the code of a process, but only the recently used part of them. So swapping is still used for optimize the usage of the main memory. Okay, so this is schematic view. Typically, you need enough memory. Typically, you have 3 regions, not 2, in the sense that one region is used for running the current process, one for swapping out the old one, and meanwhile another image is swapped in. But it depends on the strategy. Second important point. Of course, if I had to implement an hardware structure for memory and software in the kernel for managing memory, the first idea that I have in mind is that the locations are contiguous. So the first instruction is at 0, then at 4, 8, etc. Okay? This is the logical view of the address space for instructions and data. This is okay, but it has many problems because in a multiprocessing system, what happens? Well, first of all, each process needs to be protected with a relocation register and limit or base and decimal stream. But the problem is the one illustrated in this slide. Suppose that you have the kernel that has scheduled these 3 processes. This is the memory layout for these processes. Now suppose the process 8 terminates, of course it frees this region of memory, or contiguous memory. Then process 9 is smaller in size, so it can be allocated in this region. Then process 10 be allocated, and so on. But maybe another process cannot be allocated contiguously here. Okay. Moreover, how the kernel decides where to put a new process, because this is the simplest view. But in the long run, you will have a lot of holes. Okay? And depending on the strategy, you will fill the holes typically in 3 ways. First fit, so you keep the holes ordered by address. The first hole that is able to contain the new scheduled processes is used. Or the best fit, so you keep them in increasing order of dimension, or vice versa, the worst fit, which is the rationale behind these strategies. By simulations and experience, first fit and best fit are better than worst fit in terms of speed and storage utilization. So why don't we use the best fit? That seems to be the most reasonable. Because the best fit, by definition, leaves small holes. By definition, okay, that's why someone was not fool to propose a worst fit. Worst fit means that I leave large holes so that large process may find their continuous location. By the way, the real problem is that after some time, the memory will be like Guerriera says, with a lot of holes, and the only way to allow new processes to be scheduled is to compact memory. So to fill these holes. But this operation is expensive because we have to move one byte after the other. So this is called the fragmentation problem. So there is some space in memory that cannot be used only because we have all these spread different address of memory. There are some additional problems that you cannot move something that is being filled by the DMA, for example, because you are transferring in memory some data. Now the solution is paging. The solution is paging. What does mean paging? That the logical space of programs and data is divided into fixed side pages. So the key concept is that the page has a fixed dimension, typically a power of 2. Okay, normally the dimension of a page depends on the fragmentation that we desire, but the key point is since paging is then used for virtual memory, it depends on the speed of the disk and the dimension of the disk. So that's why in the old time you had small blocks, and today you have 8 kilobytes for dimension of the pages. So the programs, the logical memory, and the physical memory is divided into pages for the logical and what I call frames. Okay? So the physical memory is divided into frames. Memory, and these are the frames. Frame 0, 1, 2, 3, etc. All of the same dimension. And the logical address space 2 is divided by into a number of pages. So the last page, for example, for a program, on average will be half empty on average. So this is a fragmentation, internal fragmentation, but we accept this internal fragmentation because we have a lot of advantages for using pages. As you can imagine the using paging, we can avoid to store continuously the logical in the physical space, the logical space of a program. So it's like having my program divided in small pieces of the same dimension, and I can put these pieces in memory in different frames, not contiguously. Okay? Since these tiles are all of the same dimension, you can put them wherever you want. Okay, so the concept of paging is same dimension and power of 2, we will see why. Now, the problem is that the hardware becomes more complex because you need, by hardware and also the software, to manage what is called a page table. Page table that maps the current physical frame to the logical page. This is additional memory, kernel memory that you need to use. So why we use pages that are power of 2? Because the address generated by the CPU is interpreted by the memory management unit in this way. You have a first field devoted to the page number, and the second field that is the page offset. So if a page is of 1 kilobyte, you need 10 bits here. 10 bits, because 2 to 10 is 1 kilobyte. And if you have, say, 32 bits for the others, the remaining 22 are page numbers. So with a 32-bit architecture, you may have 2 to 22 pages of 1 kilobyte, or if it is typically 4 kilobytes, takes 12 bits, and 20 are the bits for the page number, so you can have 2 to 20. It means 1 million pages. Okay, so this is the logical translation mechanism. So the kernel, there is a page table. There is one page table for each process. And the CPU generates 32 bits. The first part is the page number, the second is the displacement or offset. Hidden here, there is a register that points to the beginning of this page. When a process runs from the switching, the kernel fills this register that is not shown here with this address. Okay? So add a register here. So the translation mechanism is to take this number, say 4, as an offset in the page table. The page table contains the frame number. So where is now in physical memory this page? So this frame F contains this page, and then simply adding to this number the displacement, the offset. So if F points here and D is here, it go at this byte. Okay. So just before finishing, which is the main advantage is that we can simply changing this F here, change the location, physical location of the pages. Which is the disadvantage in this simple architecture is that using exactly this scheme as an overhead of 100%. So if the access time to memory is say 10 nanoseconds, it will take 20 nanoseconds because you must read this F and then finally the byte. Okay? So this is an overhead of 100%. So slow down the access to memory of 100%. So this is not acceptable, and so we will see the solution. But just to finish, you see logical memory, page 0, page 1, page 2, page 3. Probably this is half empty. Currently, a snapshot, the kernel has loaded the page 0 in frame 1, page 1 in frame 4, page 2 in frame 3, and so on. So, all the reference to physical memory must pass through the page table. And 1, you see that is page 0, page 1 is here. But there is no contiguity. Okay? This is made transparent by the hardware through the memory management unit that uses the page table.
Excuse me, can you repeat the disadvantage?
Disadvantage? Exactly this. Where is this page table stored? In? It's around the world. Where is it? In memory. In particular, which memory? In kernel main memory, kernel memory, of course. Otherwise, people will play with this number. It's in kernel memory, but it's in main memory. Okay, so using this mechanism, it means that you have to read first this to get this number here. You have first to read this number, then to add the displacement, and finally to read again in memory. So you have to read in memory, 100%. You know perfectly the solution. Someone knows the solution to this. Otherwise, you will go back to the computer architecture course. Okay. Keep this surprise for after the interval. Okay.